Welcome you all for the second lecture on complex analysis. In the previous lecture, we will discuss about the introductory part of complex number and the properties of a complex number and representation of a complex numbers in Cartesian as well as polar form. In this presentation, we will discuss about the starts with the functions of a complex variable. First, let us define a complex function. We can define in let w is equal to f of z and can be expressed in terms of u of x comma y plus I into v of x comma y. The Cartesian form here x and y where u and v are the real valued function means w can be expressed in terms of u plus iv. U plus iv is equal to u and v are the functions of x and y. Also, w is equal to f of z can be interpreted as a mapping or transformation from one plane to another plane. Means here z plane to w plane. Means you can see here, this is a z plane. In the z plane, we have x and y coordinates. In the w plane, we already told it is in uv plane. U and v will be the real and v is the imaginary axis. Here, there is a function or a mapping from w is equal to f of z means here the x and y changes to a the domain of a function to range of f here. This is the representation of function is defined in complex variable. We will give one example related to this. Find the image of real part of z is equal to 1 under the mapping f of z is equal to z square. Here, given that f of z is equal to z square means here first we can z is a it is in the Cartesian form means x plus iy. Z can be expressed in terms of Cartesian means x plus iy the whole square. If we expand this, it is a plus b the whole square form, that is x square minus y square plus 2i into xy. 2i into xy, then you can f of z means it is u plus ib. Means u and v are the functions of x and y. You can separate the real and imaginary parts, left and right hand side, then that become u of x comma y is equal to x square minus y square and v of x comma y is equal to 2xy. If you observe that the image, the line is given real part of z. What is real part of z? Real part of z means x is equal to 1. And also x is equal to 1 means you can substitute here x is equal to 1 means u is equal to 1 minus y square. Similarly, here v is equal to 2xy means x is equal to 1 means v is equal to 2y. If you put it here, you can substitute y is equal to v by 2. This becomes v is equal to v by 2. Then u is equal to 1 minus v squared by 4. Similar way, we can say that here v square is equal to 4 into 1 minus u means it is a parabola. You can see here it is a parabola. Then you can observe here this is a given line. This line after the transformation the mapping is given w is equal to z square. Using the transformation you get a parabola at u is equal to 1 minus v squared by 4. This is the diagram of a in a w plane. This is the mapping line become transformed into a parabola. Now we will discuss the calculus part of a in a complex plane. First we will discuss about a limit of a function. Suppose the function f is defined in some neighborhood z0 except possibly at z0 itself, then f is said to be possess a limit at z0 written as limit of z tending to z0 f of z is equal to L. Exactly similar way how we define in a real analysis. Here also we discuss in terms of complex plane. If for every epsilon greater than 0, there exists a delta positive such that mod f of z minus L limit is less than epsilon whenever 0 less than mod z minus z naught is less than delta. This is known as epsilon delta definition of a limit of a function. And also there are some properties related to limit function, that is limit of sum, product and quotient. Suppose limit z tending to z naught f of z is equal to L1 and limit z tending to z naught g of z is equal to L2, means there are two limit function, limit of a sum. If you make sum of these two limits z tend, because the limit value approaching to z tending to z naught, then you get L1 plus L2. Similarly, if limit of z tending to z naught f of z into g of z is equal to L1 into L2. And the quotient limit of z tending to z naught f of z divided by g of z is equal to L1 by L2, but here denominator limit not equal to 0. Now we will discuss about the continuity of a function. We say that a function f is continuous at z0 if limit of z tending to z0 f of z is equal to f of z0. A function f is said to be is defined by f of z is equal to an z to the power an minus 1, means here this is the polynomial of degree n where n is a non-negative integer and each a1, a2, etc. ai is not equal to 0 and I is running from 0 to n are all complex constants. Now we will discuss about the derivative or differentiability of a function. Suppose a complex function f is said to be defined in a neighborhood of a point z0. The derivative of f at z0 is denoted by f dash z0 is equal to limit of delta z tends to 0 f of z0 plus delta z minus f of z0 divided by delta z. If the limit exists, then only this is known as the function derivative exists. It is exactly similar way what you are learned in the first principle of differentiation in your PU classes. If a limit in 3 exists, then only f is said to be differentiable at z0. Also, you must remember if f is differentiable at z0, means f is continuous. You must remember here, means if you come to the second semester course, means definitely you are passed in the first semester course. That is the meaning. Means f is differentiable, means it is a bigger space. It is more complicated, means continuity, then you can differentiability, then higher order will becomes. Now we will discuss some rules of differentiation. Whatever you learned in your real analysis, exactly here also the rules are follows, that is constant rules and sum rules and product rules. Here d by dz of c constant is equal to 0 and d by dz of f of z plus g of z means that can be expressed as f dash z plus g dash of z, and d by dz f of z into g of z means first function you can take as it is and second function can be differentiate, then second function can be taken as it is and differentiate the next one. Quotient rule means d by dz of f of z by g of z means denominator square. Then in the numerator, you can keep denominator as it is, differentiate the numerator minus keep as it is the numerator and differentiate the denominator. That is the quotient rule. Same in the real case. Here also complex case is also follows. And chain rule, you know that the function first outer function can be differentiated, then you differentiate the inner function also. And d by dz of z power n is a standard form n into z to the power of n minus 1 where n is an integer. Here are some simple example about the differentiability of the functions. Here f of z is equal to a polynomial function 3z to the power of 4 minus 5z cube plus 2z. Exactly similar lines what you learned in your reals analysis. Same way here also we differentiate, but here all polynomial functions are continuous in general. Here f dash z is here z power n forms 12z cube minus 15 z square plus 2, the derivative of this function. Here it is in the form of quotient, then you can take apply quotient rule here 4z plus 1 the whole square, keep as it is the denominator, differentiate the numerator, that is z square derivative is 2z minus keep as it is z square and differentiate the denominator means 4 because 1 is a constant. If you simplify, you get a result for this. Here, nowhere differentiable. So that means first you can take with delta z is equal to delta means small increment z to delta z means delta x plus I times delta y. Means the function f of z plus delta z minus f of z, because if you differentiability definition limit of delta z tends to 0, f of z plus delta z minus f of z divided by delta z is the differentiability definition. We can apply here the numerator become delta x plus 4i into delta y into 4x plus I times delta y. If you delta z tends to 0 means delta x plus I times delta y is 0. Means denominator is 0 means here it is not. If you take let delta z tends to 0 means along a line parallel to x axis. Then delta y is equal to 0 means the value is 1. On the other hand, if you see that delta z tends to 0 along the line parallel to y axis, you can see along the line parallel to an x, means this is 0 means you get delta x by delta x that become 1. If delta x is equal to 0 means you get 4. Therefore, f of z is not different because in the differentiability definition, left hand derivative is equal to the right hand derivative. Therefore, the previous example shows that it is nowhere differentiable. Now we will hear this the important concept we will discuss in the complex analysis. That is one of them is analytic function. Means first we discussed about the limit, then continuity, then differentiability. The more appropriate is analyticity. Analytic means any complex function w is equal to f of z is said to be analytic at a point, some point z naught, if f is differentiable at z naught and at every point in the neighborhood of z naught. Means wherever the point is there, the neighborhood is also it is differentiable. Then only we say that it is analytic. A function is we say that it is analytic at every point z is said to be an entire point. We must remember all polynomial functions are entire functions. Here, because we cannot check each and every point is analytic. In this way, there are two scientists are described. They are derived one of the important equation that is known as Cauchy-Riemann equations in analyticity. Means instead of checking each and every point differentiability, we can use this Cauchy-Riemann equation and solve analytic function. The statement of a Cauchy-Riemann equation is, suppose f of z is equal to u of x comma y plus I into v of x comma y is differentiable at a point z is equal to x plus iy, then at z, first order partial derivatives of u and v exist and also satisfies this equation, that is dou u by dou x is equal to dou v by dou y and dou u by dou y is equal to minus dou v by dou x. Means this can also be represented in ux is equal to vy and uy is equal to minus vx. How to prove this theorem? What is given here? There are three fundamental things we must remember whenever we are proving the theorem. First, you can see that the theorem, what is given, what is the given, what is to find, then how to find, and what are the relationship, the necessary things needed for proving the theorem. These are the 4 points you must remember for proving the theorem. In this theorem, they are given that the function is differentiable. And also, the first order partial derivatives are given, exist. Then, after getting this, then this equation holds good. Means first point is the function, given function is differentiable. We can start with this given that f dash z is exist. F dash z is exist means it is a differentiability. Means we know the definition of differentiability at z naught. Then f dash z is equal to limit of delta z tends to 0 f of z plus delta z minus f of z divided by delta z. Now we are proving in a Cartesian form. That's why we can write f of z is equal to u of x comma y plus I into v of x comma y. And also z is equal to x plus iy means if you change z to delta z means definitely that z is a function of x and y means x and y is also some change will be occur. That is delta z become delta x plus I times delta y. Here if you change this become f dash of delta z, that is u, first we can u of x plus delta x, y plus delta y and v I into v of x plus delta x comma y plus delta y minus of u of x, f of z means u of x comma y plus I into v of x comma y. If you take remove the brackets, then it become minus sign. And also delta z become delta x plus I times delta y. You know that it is from one of them is in the real, another one is in the imaginary. X is the real axis and y is the imaginary axis. Then since the limit exists means delta z can approach 0 from any direction. First, we will take particularly if delta z tends to 0 horizontally, then delta z is equal to delta x and delta y becomes 0. If equation 3 become f dash z become, here you can see that this delta y is 0, here also delta y is 0, this is also delta y becomes 0. Then the equation become here this become u of x plus delta x comma y minus u of x comma y, and another equation is v of x v of v of u of x plus delta x comma y minus u of x comma y divided by delta x plus I times limit of delta x tends to 0 v of x plus delta x comma y minus v of x comma y divided by delta x. You know that it is the fundamental definition of first order partial derivative with respect to u here, and this is the first order partial derivative with respect to v v with respect to x here, means that can be written as f dash z is equal to dou u by dou x plus I times dou v by dou x. You call that as equation 5. Similar way, if delta z tends to 0, vertically means delta x becomes 0 and delta z is equal to I times delta y. Means the equation 3 become x comma y plus delta y minus u of x comma y divided by I into delta y. You know that complex number cannot be present in the denominator, means what happens 1 by I means conjugate can be multiplied, then numerator and denominator that become minus I divided by I square. I into I is I square, that become plus, you get here minus I here. Minus I, this I become cancelled. Again, this is a partial derivative with respect to u with respect to y. Here v with respect to y means that is the definition of partial derivative, means f dash z means minus I into dou u by dou y plus this is dou v by dou y. Means you know that equation 5 and 6. Equation 5 and 6. If you observe that left hand sides are same, then right hand side is also equal. We already discussed in the first lecture, if two complex numbers are equal means real part is equal to the real part of the other, imaginary part is equal to the imaginary part of the other one, means here if you see dou u by dou x is equal to dou v by dou y. Similarly, dou u by dou v by dou x is equal dou u by dou x is equal to dou v by dou y, means ux is equal to vy and uy is equal to vx, means this is the theorem statement of a Cauchy-Riemann equation. Ux is equal to vy and uy is equal to minus vx. And conversely also we can prove easily from the Cauchy-Riemann equation. And I will give you the hint to prove the polar form of a Cauchy-Riemann equation. Suppose in place of x and y, r and theta are the quadrants, r comma theta. Then if you replace r comma theta in this function, u of r comma theta plus I into v of r comma theta is differentiable at z is equal to r into e power I theta exponential form. Then z having a first partial derivative with respect to u and v exist, then Cauchy-Riemann equation ur is equal to 1 by r into vr and minus u theta and u vr is equal to minus u theta. Cauchy-Riemann equation in polar form, ur is equal to 1 by r v theta and 1 by r u theta is equal to minus vr. Thank you. We will discuss in the next class.